Welcome to This Explainer. Look, if you're a developer hunting for a totally private, absolute paradigm shift in local agentic coding, you've landed in the exact right spot. Today, we're tearing down Ornith 1.0. It's this brand new family of open source models built specifically for complex coding tasks. And honestly, the best part? You can run the whole shebang locally, for free, on your own hardware with absolutely zero internet connection required. No more bleeding money on API costs or sending your proprietary enterprise code out into the cloud. We're going to break down exactly how this model family works, why it punches so incredibly far above its weight class, and most importantly, how you can actually set it up as your ultimate offline coding companion.
So here's our agenda for today's deep dive. We'll start with the power of self-scaffolding, look at the 9B versus 35B benchmarks, jump into local OS deployment, examine the 3-layer safeguard system, and wrap up with troubleshooting common errors.
The absolute core differentiator of the Ornith model family comes down to this. Most models just learn to write the answer. Ornith, though, it learns to write its own plan first. Up until now, models have basically been trained to just spit out an answer as fast as humanly possible, right? But Ornith, which is actually built on top of the Qwen and Gemma architectures, does something way smarter. It's kind of like a bird building a nest before it lays an egg. It has this extended thinking phase where it builds its own setup, its own plan, and its own structure before it even attempts to solve a single line of logic.
Section 1. The power of self-scaffolding.
So it's absolutely crucial to understand what self-scaffolding actually looks like in practice. Think of the model as acting as its own context engineer. Traditionally, us human developers, we've had to sit there and write manual test harnesses just to guide an AI agent through a complex task. While with Ornith, the model literally writes the harness itself on the fly. If you toss it a prompt without an API key, for example, its scaffold will plan out the constraints, figure out alternative bypass routes, write the testing criteria, and lay the entire groundwork, all before executing the final script. It is an entirely new level of autonomy. To pull this off, Ornith uses this really clever two-stage reinforcement learning process. First up, the model proposes a task and an initial scaffold, or harness. Next, it proposes a rollout solution based entirely on that scaffold. And finally, it evaluates multiple rollouts and uses a reward signal, specifically Group Relative Policy Optimization, or GRPO, to update the model's weights. Basically, what this means for you as a developer is that every single training step made Ornith better at two things at once: building a bulletproof game plan and executing a flawless final solution.
Section 2. 9B versus 35B benchmarks.
Let's put the 9B and 35B variants head-to-head on some complex agentic coding tasks. On Terminal Bench, the 9B model scores a highly respectable 43, while the 35B hits a massive 64. But over on SWE Bench, the gap is surprisingly tight, 69 for the 9 billion parameter model and 75 for the 35 billion. To put that into perspective, what these numbers are proving is that, yeah, the 35B is an absolute powerhouse for heavy-duty software engineering, but the 9B model, it's putting up numbers that rival other open-source models literally more than 3 times its size.
And honestly, that brings us to the sweet spot. For anyone running commodity hardware, the 9B model is the absolute go-to. It punches so far above its weight class on bounded logic, if you just needed to write a specific Python function, fix a bug in a codebase, or build a small module, the 9B model is going to process that quickly and accurately on standard hardware. It leaves your RAM and GPU breathing easy while still delivering frontier-level structural logic.
Section 3. Local OS deployment.
Okay, here is your concrete setup checklist. First, you're going to want to grab the GGUF format of the model, since that's heavily optimized for consumer GPUs. You can easily serve this via LM Studio or just run a standard terminal command like alama run Ornith 9B. If you like a bit more granular control, you can spin up a VLM server directly from your command line. But listen up, because here is the absolute most critical step. Because Ornith builds its own scaffold, it generates a massive chain of thought. You must, and I mean must, increase your max model length, your context window, to at least 64K tokens or higher. If you just leave it at the default 8K or 16K, the model is going to spend its entire context window just thinking and planning, and it'll suddenly just stop before it actually writes the code for you.
Let's just pause for a second and appreciate the massive benefit here. Once this is set up in your local environment, you have an agentic coder that is 100% offline. You can literally unplug your router, turn off your Wi-Fi, and it will still perfectly read your local files, write tests, and execute fixes. Zero API costs, uncompromised privacy. Your proprietary enterprise code never, ever leaves your machine. For private coding environments, this is just a total game changer.
Section 4. the three-layer safeguard system.
Now, you might be wondering about this theoretical problem. If the model determines the rules for its own test, why doesn't it just, cheat? We call this reward hacking. A lazy model might figure out a shortcut, like, say, just hard-coding the expected output from a visible test file instead of actually writing the complex sorting logic you ask for. Sure, it passes the test, but the code is totally useless to us.
So, to build a rock-solid defense against that exact problem, Ornith was trained with a 3-layer anti-cheating system built right in. Layer 1, the environment is immutable. The model is strictly sandboxed and simply cannot modify the verification scripts to make its life easier. Layer 2 is a deterministic monitor that actively watches the agent's tool use. If it tries to access unsanctioned tools, it uses built-in feedback tools to instantly penalize the action, forcing the model to self-correct on the spot. And finally, Layer 3, an LLM as a judge, acting as an overarching supervisor with absolute veto power. If the model finds some sneaky shortcut that the monitor somehow misses, the judge LLM steps in, fails the attempt, and ensures honest execution.
Section 5. Troubleshooting common errors.
Now, because Ornith is a highly advanced reasoning model, it heavily utilizes specific tags, things like thought blocks or tool call blocks under the hood. If you start seeing raw reasoning text bleeding into your final code output, or if the agent keeps failing to trigger a web search or a file read, it just means your runtime is stripping those tags out. The fix is strictly manual, but it's super simple. You just need to update your chat template in your server settings, and actually if you're using VLLM or SGLang, make sure you have the proper reasoning and tool call parsers enabled in your configuration. I do want to remind everyone watching, though, that while Ornith 1.0 is highly capable, self-correcting, and totally brilliant at bounding logic, AI is still AI. As one of our sources wisely pointed out, faster and prettier doesn't necessarily mean more faithful. The model might confidently skip a nested edge case without telling you. So human oversight isn't quite obsolete yet. A manual verification loop remains a non-negotiable requirement for safe software deployment. Always double-check.
Which brings us to our final thought for this explainer. We are entering an era where the AI doesn't just solve the problem, it actually designs the testing environment to prove it solved it. If models like Ornith can scaffold, test, and self-correct on local hardware completely without our help, what exactly is the true role of the human software engineer going to be 5 years from now? Will we just be the final signature on the deployment approval? It's definitely a fascinating shift to ponder. Thanks for joining me on this deep dive, and keep experimenting with those local environments.